Welcome to this explainer. I am your strategist, and today we are tackling a massive, incredibly frustrating challenge that trips up literally thousands of students every single year. You know the feeling, right? You memorize the formulas, you read the textbook, but then you sit down in the exam hall with a Cambridge pass paper, whether your syllabus code is 0625, 0651, 0652, 5054, or 9702, and suddenly the questions look totally alien. You're staring at the page wondering, what do they actually want from me? Well, you are definitely not alone. I see two types of students all the time. Let's call them Alex and Sam. Now, Alex overloads their answers. Alex dumps every single raw physics fact they can remember onto the page, but includes absolutely zero analysis. They write a whole novel for a 2-mark question and still lose points. Then you have Sam. Sam rushes. Sam completely misses the command word requirements they describe when they were supposed to explain, or they just write bullet points that don't connect. If you looked at their papers, you'd see a sea of red pen marks. But today we're changing that. We're going to get inside the examiner's head. We're going to transform your raw theoretical knowledge into a precise, bulletproof exam strategy so you can decode real syllabus scenarios and rack up those top marks.
Okay, let's look at our roadmap for this session. First, the secrets of circular motion. Second, decoding Hooke's law graphs. Third, balancing forces and moments. And finally, mastering pressure and area. Let's jump right into the content.
Section 1. Secrets of Circular Motion.
Now, there is a fundamental concept in circular motion that examiners absolutely love to test. Why? Because it feels completely counterintuitive. We naturally think that if an object is moving at a perfectly steady speed, it cannot possibly be accelerating. But remember, in physics, velocity is speed in a particular direction. It is a vector. That means a change in velocity can mean a change in speed, or a change in direction. So if an object is moving in a circle, its direction is constantly changing, meaning it is constantly accelerating. And if it's accelerating, there must be a resultant force. Now look at this exact textbook question. A car travels around a bend in the road. What supplies the centripetal force needed? How would our student Alex answer this? Alex would probably write a massive paragraph deriving the formula for acceleration. Sam might just write gravity. Both get 0 marks. To beat this, you need to decode the command words and use the Peel framework: point, evidence, explanation, link. Top students structure their answers this way. But before we continue and reveal exactly how to apply that framework to this question, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's look at how to actually answer this using our framework.
Here is the physical mechanism in action and how you should explain it to the examiner. When a car or a motorcycle, like the one we see in this diagram leaning heavily into the turn, goes around a corner, it is the sideways friction between the tires and the road that provides that necessary inward force. So your point is identifying the force, friction. Your explanation is why it matters. Without this friction, Newton's first law of motion predicts the vehicle would just continue traveling in a perfectly straight line. The tires grip the track, generating a frictional force pointing directly towards the center of the curve. This constantly pulls the bike away from its straight-line path and forces it into a circular one. If they hit a patch of ice and that friction breaks, the bike doesn't magically fly outward. It just travels straight off the curve at a tangent. This is how you secure full marks, by identifying the exact, real-world mechanism.
Let's cement this highly testable definition so you never lose marks on it again. Centripetal force is the inward force needed to make an object move in a circle. It is absolutely crucial to understand that centripetal force isn't a magical new type of force. It's just a label for whatever force is doing the job. It could be friction for a car, gravity for a satellite, or tension in a string. Examiners will also test your understanding of variables. You need to explicitly state that more centripetal force is needed if the mass of the object is increased, if the speed of the object is increased, or if the radius of the circle is reduced, meaning a much tighter curve requires way more grip. And let's clear up a massive misconception that costs students dearly. There is no such thing as a centrifugal outward force acting on the object itself. Do not write that in your exam. If the string breaks, it flies off at a tangent. Simple as that.
Section 2. Decoding Hooke's law graphs.
Welcome to Act 3, the transformation. Examiners love testing the mechanics of stretching springs because it forces you to interpret visual data. They want to see if you can take a physical, real-world measurement and translate it into a mathematical relationship on a graph. This is where we transform our student Sam's rushed, one-word answers into green check marks. Look at this brilliantly illustrated comparison. On the left, we have a physical spring. When a load of 1 Newton is applied, it stretches by 10 millimeters. When a 2 Newton load is applied, it stretches 20 millimeters. Now, how do we translate this for the examiner? Look at the graph on the right. Up to a specific point, marked X, the line is perfectly straight and passes directly through the origin. This is your evidence in the Peel framework. Because it's a straight line through the origin, it means that if the load is doubled, the extension is exactly doubled. Every single 1 Newton increase produces the exact same extra 10 millimeter extension. This proves that beneath its elastic limit, the extension is strictly proportional to the load.
This brings us to a calculation you must master, the spring constant, represented by K. As long as the graph line is straight and passes through the origin, the material obeys Hooke's law. That means dividing the load by the extension will always give you the exact same constant value. In our example, dividing 1 Newton by 10 millimeters gives us 0.1 newtons per millimeter. The formula is force equals the spring constant multiplied by the extension, or F equals K times X. If an examiner asks you to calculate this, you state the formula, plug in your numbers, and show your units. Knowing this constant is incredibly powerful because you can use it to predict the exact extension for absolutely any load, provided you don't stretch the spring past its limit of proportionality, where it deforms permanently.
Section 3. Balancing forces and moments. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, welcome to the interactive workshop part of this explainer. We are putting 60 seconds on the clock for Challenge 1, the data scan. Look at this complex data table tracking the speed of a falling parachutist over 9 seconds. Under exam conditions, you don't have time to ponder. You need to extract the core trend immediately. At 0 seconds, her speed is 0. By second 4, she hits 40 meters per second. But then look at second 5. Her speed suddenly drops to 25, then 17, then 12, until it steadies out at 10 meters per second by second 8. Your challenge, spot exactly when the parachute opens. Boom, time's up. It's clearly between second 4 and second 5, marked by that massive, sudden deceleration. This is how you actively read data. Let's move to Challenge 2, find the flaw. Often students like Alex will just write, "Gravity makes her fall." That sentence is losing marks because it completely ignores the opposing forces. The crucial point here, and exactly what examiners want to see, is the constant battle between two specific forces. The downward force is gravity, or weight. The upward force is air resistance pushing back. At 3 seconds, gravity is significantly larger than air resistance, creating a resultant force downwards, so she accelerates. But when that parachute opens, her surface area massively increases. Suddenly, at 6 seconds, the upward air resistance is much larger than her weight. This creates a resultant force acting upwards, causing rapid deceleration. Eventually, the air resistance decreases as she slows down, until it perfectly balances our weight, and she falls at a constant terminal velocity.
Now let's decode rotational forces, specifically the heavy bar problem. This is a classic trap. In simple problems, a bar has negligible weight, but in higher mark questions, you have to include the weight of the bar itself. Here is your step-by-step strategy to guarantee top marks. Step 1. Redraw the diagram clearly showing all forces and perpendicular distances. Don't skip this. Step 2. Place the bar's entire weight acting straight down from its midpoint, its center of gravity. Step 3. Carefully take moments about the pivot. And step 4, apply the principle of moments. Because the bar is in equilibrium, you equate the total clockwise moment to the total anti-clockwise moment. This is your blueprint.
Let's look at how this blueprint applies to a real lever system, a nutcracker. Look closely at the forces. You apply force F to the handles, but the physical force actually crushing the nut is much bigger than F. Why? Because of the principle of moments. The pivot point is the hinge on the left. You are applying force F at a very large distance from that pivot, creating a massive turning effect, or moment. For the system to be balanced, the nut must apply an equal and opposite moment. Since the nut is positioned at a much smaller distance from the pivot, the actual force there must be proportionally much larger to create that equal moment. That's the physics you need to explain. Let's analyze another classic exam scenario, the wheelbarrow. Here, the pivot point isn't a hinge, it's the center of the wheel, point A. The load, plus the weight of the barrow, acts straight down through the center of mass, point M. To lift the handles, you apply an upward force. An exam question might say, you lift with an upward force of 20 newtons at a distance of 1.5 meters from wheel center A.
calculate the moment. It's simply force times perpendicular distance. 20 newtons multiplied by 1.5 meters gives you 30 newton meters, acting anti-clockwise. To find the weight of the load, you'd equate that 30 newton meters to the clockwise moment created by the weight acting down through point M. Show every step you're working and you secure every single mark.
Section 4. Mastering pressure and area. We are now shifting focus from rotational forces to forces spread out over a specific surface. This is Challenge 3 Prep, getting your formulas and units locked in perfectly. The formula for pressure is P equals F divided by A. Pressure equals force divided by area. If force is in newtons and area is in square meters, pressure is in newtons per square meter, which is formally called 1 Pascal. Now, examiners love to test your conceptual understanding of this unit. A Pascal is incredibly small. Imagine spreading the weight of a tiny apple over an entire square meter of floor. That is about 1 Pascal. Because it's so small, practical applications use the kilopascal. Standard atmospheric pressure is a massive 100,000 pascals. Keep these scales in mind when you're evaluating if your calculated exam answer actually makes logical sense.
All right, Challenge 3, Speed Writing. You have 30 seconds to write one perfect Peel paragraph comparing football boots to snow skis. Go. Okay, here is the perfect model answer. A football player's entire downward weight is concentrated onto the tiny area of just a few studs. Because area A is extremely small, the resulting pressure P is incredibly high enough to sink into the dirt for extra grip. Conversely, snow skis take that exact same weight and spread it over a massively larger surface area. By drastically increasing the area, you dramatically lower the pressure exerted on the snow, preventing the skier from sinking. Changing the area completely changes the physical result, even when the force remains exactly the same. Did your paragraph hit all those points?
We've reached Act 5, the final system. To guarantee top marks, you need 3 rules. Rule 1, command word decoding. Know if you're describing or explaining. Rule 2, the PELL framework application. Point, evidence, explanation, link. Rule 3, the time management matrix. Don't spend 10 minutes on a 2-mark question, like our friend Alex. To prove you've mastered this, I'm leaving you with a provocative question. If our parachutist jumps again, but this time opens a parachute with a significantly larger surface area, how exactly will this affect her speed-time graph? Think about pressure, air resistance, and deceleration. Sketch that curve right now. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @theacetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.